Hello students, it's your professor Dr. Mink, and welcome to our first lecture of this class. Obviously this is an audio lecture, so if you're not hearing my voice, if you're reading that text and not hearing my voice, please stop and adjust your system volume. That's not me in that picture. I'm not that young or that handsome, sorry. Let's get started. This is just another friendly reminder that you should be reading the textbook before reviewing the slides for the particular chapter we're covering or section of chapter we're covering. This is ultra critical in an online course. I'm not saying this because I want to give you a hard time or give you busy work. It's because I know how important this is in a class where you and I are not physically present together, and you have the ability to ask questions, and I have the ability to look at you and see a puzzled look on your face and say, hey, what don't you understand? Let's explain it. So in an online course, you have extra responsibility for self-directed learning. And please, for you and for me, read the chapter before you review this particular lecture. So you should have read all of Chapter 2 before you got here and already started to formulate questions about concepts you're not sure about, review the lecture, and the slides in the lecture might solidify the concepts I'm trying to present. And then after that, if you still don't understand, you could Google the questions you have, or you could send questions to me via the forum or email them to me. Okay, sorry about that. I'll tone it down moving forward, but this is an important part of the process, okay? Let's get started with part 2 of chapter 2. And how about that textbook? Here's a picture of the cover of the textbook we'll be using, Problem Solving with C++ by Walter Savage, 9th edition. There are tons of demo files that accompany this textbook. So when you're in a chapter, let's say chapter 2, and you see display 2.6, if you go to the files that I give you with each chapter, display 2.6 is a code file. It's a source code file. We'll get to that in a second. So you'll be able to download and run that code file as you're reading the textbook. If you have questions, I'm here to support you, but this is an integral part of the learning process. The textbook is, especially in an online class, is of paramount importance. Before we get started with the content of this course, I want to walk you through downloading the free development environment, the compiler that we're going to be using for this class. It comes from Microsoft, and there is a free version that you can run on a PC, and the requirements are rather minimal. So you'll see the top horizontal red arrow pointing to the URL that you need to go to, and then the vertical down arrow pointing to the Visual Studio Community 2019 version that you will download. It is free. If you select the professional or the enterprise version, you're going to get a short trial period, and then you're going to be required to pay a lot of money to continue with a compiler that we're not going to utilize in this class. So please be careful. Now, if you have a Mac, I've put a link to an online compiler that you could use for C++ for this class, so all is not lost. However, I'm going to be walking through most of the demos using Visual Studio Community. You shouldn't have a problem, but who knows? It's just a slight bit different. When you begin downloading Visual Studio Community 2019, you'll be asked to select which workloads. And you can see the three that I have already installed. These are screen prints of my install because I can't do a second install. It's already installed on my computer. So you're going to want the .NET Desktop Development, Workload, Universal Windows Platform Development, and Desktop Development with C++. Okay, we're going to get started now. This lecture covers Chapter 1, Introduction to Computers and C++ Programming. C++ programming is a wildly popular object-oriented programming language. I learned C++ in, I want to say 1993, 93 or 94, so roughly 20 years ago, and it has gained in popularity since then, and it is probably the most popular engineering and scientific programming language used today on the planet. This lecture includes an overview of computer systems, programming and problem solving, an introduction to C++, and we'll be using the Visual Studio 2010 IDE, Integrated Development Environment, and Visual C++ 2010 to write programs in this class. And we'll also talk about testing and debugging in this chapter. In the first section, we'll have an overview, a review of computer systems and how they handle data and their general purpose. This is review from previous classes. If you've taken computer literacy or introduction to programming or any other class, you've probably seen this material before, but it's important to make sure we're all on a level playing field before we start programming. So let's go. A computer will only do exactly what we tell it to. And in order for a computer to perform tasks, behind the scenes has to be a program written to accept input from the user, process that input per the instructions in the computer program, and generate output. So a computer program, simply stated, is a set of instructions for a computer to follow. Computer software is the collection of programs used by a computer. It includes editors, translators, systems managers, etc. Three main classes of computers: PCs, personal computers. I have one sitting in front of me. It's a laptop. There are also desktops, relatively small, and they are used by one person at a time. A workstation is a larger and more powerful computer than a PC. My first job out of college in 1985, I worked as a programmer for a company called Boeing, the aerospace company, and I had a very, very elaborate engineering workstation in my cubicle, and that was connected to a mainframe computer, which is the next type of computer. Very large computer, runs an entire company or corporation, requires support staff, and it is shared by multiple users. So my workstation was it probably had, in 1985, it probably had less resources than the laptop I have sitting in front of me today because of advancements. But it was a very, very sophisticated, very expensive. I remember being told it was an $85,000 engineering workstation back then. And of course, I worked in the defense industry that had very large budgets. So those are the three main classes of computers that we'll be discussing in this class. Networks are obviously everywhere in society today. A number of computers connected to shared resources. I am recording this lecture on my personal computer, my laptop. I'm actually sitting in my family room in my home, and I will use a network, one of the largest networks in the world, the internet, to upload this to a server somewhere. I think it's in Newtown, PA, but I'm not sure. That's where Web Study is located. And you will come to the college and sit in my classroom if you're taking a traditional class, and you will log into a network to our server, and you will download resources, access the internet. So a network is a number of computers connected to share resources such as printers, other devices, other computer systems, and most importantly, information. This slide discusses computer organization and the 5 main processes or components of a computer system. Input devices allow communication to the computer. The primary input device that we'll use is the keyboard, secondary the mouse. I'm using a microphone right now to provide input to the computer. Output devices, the most common output device which outputs soft copy is the monitor, speakers, etc. The processor does the work. That actually turns input into output. Main memory locations contain the running program. That's typically RAM. Secondary memory, permanent record of data, often on a disk. Although that's changing. My wife's computer just died, and we're buying her a new computer, and we're making sure we don't get a hard disk drive. We're getting a solid state drive, which is, in essence, a large flash drive. It's integrated circuits, no moving parts. It is the storage of the future, if you will. This slide provides a graphic. This is display 1.1 from the text. The main components of a computer. You see the processor, the central processing unit, and main memory are constantly working together, swapping out information in and out of the CPU, and then main memory is also swapping information in and out of secondary memory, or storage, if you will. Input is managed by the input devices and then passed to the processor, and the processor generates output. And it could be as simple as input 2 numbers, and the computer will add them together. You input the first number, you input the second number, the processor runs a computer to take the first number and add it to the second number, and it probably stores it in a third memory location, and then the program outputs that result to the monitor or to a file or wherever, some output device. We hear a lot about memory. My memory is starting to go, but that's different than computer memory. Main memory is a long list of locations, storage locations. Each contains just a 0 or a 1. At the end of the day, the processor only handles 0s and 1s, which are called binary digits. A binary digit is the smallest piece of information that a computer understands, and it is a digit that contains either a 0 or a 1. A byte, which is a piece of memory or a piece of information that has 8 bits, and we're using ASCII code, which uses 8 bits to decode each character in a program. An address is a number that identifies a memory location. Store that away, because later in this class we're going to talk about pointers, and pointers and memory address locations are very, very critical topics, but we won't get to pointers for weeks. It's in the last phase of this class, but just store that away. We'll start talking about pointers when we talk about passing reference variables, etc. Some data, most data, is too large for a single byte, to be stored in a single byte, which is 8 bits. Most integers and real numbers require more than 1 byte to be represented. So their address refers to the first byte. The address for a memory location storing an integer or a double or a float, and we'll talk about those data types soon. The address refers to just the first byte. The next few consecutive bytes can store the additional bits for larger data, depending upon the type of data that we're storing, and we'll get to that real quickly. This graphic shows how a piece of data pieces of data are stored. So, for example, the first piece of data, its location is byte 1, and it's really not byte 1, but we're simplifying it for the sake of this conversation at this point in the class. And that piece of data requires 3 bytes to be represented. So it has address of byte 1. And then there's a 2-byte location with address 4, a 1-byte location with address 6, 3-byte location with address 7. This is how pieces of information or data is stored in a computer. Now, this is greatly simplified so that it can be graphically represented, but it is, in essence, how things are stored on a storage media. Although we're used to looking at letters and numbers on computer screens, those letters and numbers are encoded using binary encoding so that the capital letter A will look like those 8 bits which make up a byte. 0, 1, 0, 0, 0, 0, 0, 1, and 65 will look like those 8 bits. An instruction may look like this: 0, 1, 0, 0, 0, 0, 0, 1. I'm having a hard time following the number of zeros across the screen. How does the computer know the meaning of that? Interpretation depends on the current instruction. Programmers rarely need to be concerned with this problem today. Back in the late 70s, early 80s, it was more of an issue than it is today. You're interested in variables that hold data, and the compiler, interpreter, and translator, etc., they handle the binary encoding. So it's less of an issue than it is today. Back in, 1984, I took an assembly level class, and it was challenging. You had to be much more concerned with memory locations and storage and how the computer encoded information. Today, it's really a non-issue, and when you get to computer organization, if you're a comp sci major, you'll talk about that, but not so much in this class. This slide tries to differentiate between main memory and the secondary memory. Secondary memory can be thought of as storage. Main memory stores instructions and data while the program is running. Secondary memory stores instructions and data between sessions. A file stores data or instructions in secondary memory, most likely a hard disk drive or a flash drive or some sort of a permanent storage device. Primary memory is not permanent, it's volatile, and when the computer loses power, powered down, the contents of primary memory is wiped clean. Secondary memory is not volatile, non-volatile. Computer might have any one of these types of secondary memory. A hard disk drive. They're fast, they're fixed and inside the computer. You don't normally remove them, although there are removable hard disk drives. Hard disk drives, in case you didn't know it, are coming to the point of obsolescence within a short period of time. Computers won't have hard disk drives, electromechanical disk drives where you actually hear a disk spinning. They'll have solid state drives, and many computers now have those solid state drives. They use the same technology as flash drives. Floppy disk, oh my, I don't think we use floppy disks anymore. Instead we use flash drives. I think you can get a 64 gig flash drive, which is a very large storage device, for under 20 bucks now. And a compact or CD compact disc, slower than hard disks, easily shared with other computers, can be read-only or rewritable depending upon how it was manufactured. Two types of memory access you should be aware of: random and sequential. Random access, usually called RAM, random access memory. Computer directly access any memory location without going sequentially through the others. One way to think about this is, if you remember VCR, video cassette recorder tapes, you had to go sequentially through the entire tape to get to a specific point, and you could think of that point as data stored in memory, maybe a scene on the movie. That's sequential access. Random access is you can go onto a DVD and you don't have to fast forward through the entire movie. You could pick a scene and go randomly, or randomly access that particular scene. The processor, typically called the CPU, the central processing unit, most likely manufactured by Intel or AMD. They're the two largest CPU manufacturers. My wife's laptop, which is sitting across the room, has an Intel processor. I have an AMD processor. These processors follow program instructions, and they're typically capable of adding, subtracting, multiplying, dividing, or moving data from one location to another. Now that sounds quite limited, but with those capabilities and the unbelievable processing speed of the central processing unit, you'd be surprised at what can be accomplished. Stay with me and you'll find out. The operating system is the software which allows the user to interface with the computer. It is a computer program. I believe much of Microsoft Windows is written in C++. Allocates the computer resources. It handles input-output processing, responds to users' requests to run other programs. The common operating systems available today: Unix, Linux, DOS, not so much. Windows, Macintosh. VMS is not a PC operating system, and we won't talk about that in this class. But right now, I would say Windows, Linux, and Macintosh are the three most popular operating systems available for computing devices. Remember the information processing cycle: input, processing, and output. Input requires a program and some data. So it might be as simple as a program that allows you to input a series of numbers, 10 numbers, 10 integer numbers. And then it outputs the average of those 10 numbers. So the input taken by the computer program accepts 10 integers through the keyboard. There's some processing that takes place. It adds all the numbers together, divides them by the number of inputs, which would be 10, calculates the arithmetic average, and then it displays it to the screen. Here's a very simple graphic of a running program. The computer is interfacing with the program, and the data is being input. Various input devices include a keyboard, mouse. Right now I'm inputting information via a microphone. It's being processed and it's being stored digitally as I believe it's a WAV file. Probably Windows Media file. And then the computer accepts the program and the data. The program processes and generates output. In this class, we're going to study a high-level programming language. Obviously, it's C++. These languages resemble human languages, and you're going to laugh when we start looking at syntax because, yes, they do, but it's somewhat cryptic. They're designed to be, I guess this is relative, easy to read and write. At your level, you'll probably think it's very difficult to read and write until you become familiar with the syntax or the grammar. They use more complicated instructions than the CPU can follow. The CPU only accepts zeros and ones, and we'll get to that later. So the program is then compiled and translated to executable code, zeros and ones, for the computer, the CPU, to execute. Some common programming languages: C, C++, Java, Pascal, Visual Basic. I'm actually teaching Visual Basic and C++ this semester at the same time. Fortran, oh my, I learned Fortran back in the 1980s. I know, many of you weren't born then. COBOL, Lisp, Scheme, oh boy, these bring back memories. C#, and Python. You may have heard of some of these. Some of these are legacy programs. You don't see Fortran used very much anymore. Lisp and Scheme, I haven't seen since graduate school. COBOL, still around. It's been around forever. C++, Java, Visual Basic, Perl, and Python are all very contemporary, widely used programming languages today. Low-level languages do require the programmer to be aware of the memory locations. I took an assembly language class, and it had to be 1983 or 1984, way back, 30 years ago. And this is what an assembly language command looked like: add X, Y, place the results in Z. And assembly language is not executable by the CPU. Assembly language still was the first low-level programming, well, one of the first low-level programming languages, and it still had to be translated to machine language, which is zeros and ones. The CPU can only follow or execute machine language, zeros and ones. So add X, Y, and Z might translate to those four binary programming steps you see on this slide. I can't remember if that's the case, and I'm in the middle of recording this. I don't want to check to see that they're the actual codes for add X, Y, and Z. This is an excellent opportunity for you to pause this instructional video and go to watch how to create your first project. It is a step-by-step video I created to help you get started with Visual Studio. Watching these videos is really important to your success. I've made them short enough that you're not going to be overwhelmed or bored, but they're long enough to include the level of detail you need to get started, and you can watch them over and over and over again. So please go watch that first video now and then come back to this lecture, and I promise you, you'll be further enlightened. Thanks. Now we're starting to get into some significant terminology that you will need to be aware of. A compiler translates high-level language, such as the program we'll write in C++, translates that to machine language. Two important terms for you to be familiar with. Source code is the original program in a high-level language, and we're going to have .cpp files, C++ files that we will write in the C++ editor as our source code, and then that code will be compiled, and the object code is the actual translated version of our program that runs in machine language and the CPU processes. This slide shows a basic outline of the steps for compiling and running a C++ program. You have in gray the C++ program, the source code, and the compiler along with the source code uses the computer to generate a machine language program that can be run, executed, and when that machine language program is executed by the computer, it most likely will, no, almost definitely will ask for data from the user, keyboard, file, any kind of input device. And that computer will run the machine language. The machine language code will run on the computer, accept the data, process, and output the results. Obviously, there are some programs that we will use, such as input and output routines, that we don't want to have to compile them each time we write a new program. So their object code, the already compiled code, is available for us to use. And this requires a linker. A linker combines the object code for the programs we write and the object code for the pre-compiled routines, classic example, input and output routines, into the machine language program that the CPU can run. This slide shows the preparation for a C++ program to run. There's the source code, the C++ program. It goes through the compiler and generates object code for the C++ program, and then the linker pulls in the object code for the pre-compiled routines that you're using, and then the final step is generating the complete machine language code that is ready to run. That's the executable program. Some brief and oblivious historical notes provided by the author. The first programmable computer was designed by Charles Babbage. He began work in 1822, but it was not completed in Babbage's lifetime. It was a conceptual or theoretical endeavor, and the first programmer was Ada Augusta, the Countess of Lovelace. Love that. He was a colleague of Babbage. If you remember, some of you, most of you are probably a lot younger than me, but there used to be a chain of computer stores called Babbage's in, well, I know there was one in the Echelon Mall, which is in Voorhees, New Jersey. And I remember visiting other malls in other cities and every once in a while seeing a Babbage's store. That was named after Charles Babbage. And there is a programming language called Ada, which I had to work with in grad school, and I absolutely, I won't say I hated it, but I disliked it. This is the conclusion of section 1.1, not the conclusion of the chapter. This is basic overview of concepts you should be aware of before we start talking about programming. Here's some questions you should ask yourself. Can you list the 5 main components of a computer? Can you list the data for a program that adds 2 numbers? Can you describe the work of a compiler? Can you define source code? That's the code we're going to write in C++. Object code is the executable, the code which is executable by the processor, the program that actually runs. and describe the purpose of the operating system, it being a traffic cop handling input, output, processing, storage, the interface between hardware and the software and the end user. Now, my friends, the fun begins. I'm so excited. We're going to start talking about programming and problem solving. I know you've waited patiently for this, and hopefully if you're 1/10 of a nerd as much as me, this will be exciting, fun, and you'll enthusiastically embrace learning the programming language of C++. Let's get going. Some basic terms. An algorithm is a sequence of precise instructions that leads to a solution. And algorithms are very useful planning tools in writing a program. And a program, or an algorithm, is then easily translated to a program, which is simply an algorithm, the steps, a sequential and precise set of instructions that is expressed in a language the computer can understand. Well, actually, that can then be compiled, translated to machine language, which the computer can understand. This slide gives an example of an algorithm which could be easily translated into programming statements. This is an algorithm that determines how many times a name occurs in a list of names. So number one, get the list of names. That would be input. Get the name being checked, probably an input statement. Set a counter to 0. Do the following for each name on the list. Compare the name on the list to the name being checked. And if the names are the same, then add 1 to the counter. And you go through the entire list. Now remember, computers are very fast. So this sounds very easy, but what if the list has 7,283,362 names? No big deal. A computer will handle that in a second, less than a second. Announce that the answer is the number indicated by the counter. So if you have that list of 2 million, whatever that big number was I mentioned, that list gets input to the computer very quickly. Maybe it's in a file, maybe it's in a database. The user types in the name they're looking for. This is kind of, the find command in Microsoft Word, and the computer very quickly can process every single name, comparing it 2,873,283 times to the name that was input, the name you're looking for, and each time it finds it, it increments the counter by 1. Very, very simple program for the find command in almost any word processor you've ever used. Programming is not an exact science. It's a creative process, and there's no concise or comprehensive set of rules for creating a program. So this becomes a challenge when I'm grading students' projects, because two students can go about the same task different ways and both get the same exact results, and one would not necessarily be more correct than the other. One might be more efficient than the other, and I'll make comments about that. But this slide talks about the program design process and two specific and important phases: the problem-solving phase, and the end of the problem-solving phase should be an algorithm similar to the one we looked at on a previous slide that solves the problems, a step-by-step approach to solving the problem. The second phase is the implementation phase, and the result is the translation of the algorithm into a programming language, and in this class it's obviously going to be C++. So we've designed an algorithm. This is what we're going to do step by step. These are the problems, these are the solutions, this is the input, this is the processing, this is the output, and during the implementation phase we translate those human statements into syntactical statements within the programming language we'll be using, which once again is Visual C++. Let's drill down on the problem-solving phase. You need to be certain that the task is completely specified. All too often, people start to write a program to solve a problem, and they haven't completely identified all the aspects of the problem. Some questions you need to ask yourself: what is the input? What information am I looking for in the output? And how is the output going to be organized? The best way is to develop the algorithm before implementation. Experience, and trust me on this, it sounds easier to just go in and start coding, but in the long run, that is an inefficient way of doing this. Students that get programs done quickly typically do write algorithms and then translate them into program statements. Experience shows that writing algorithms saves time in getting your program to run. And then you test the algorithm for correctness and move on. The primary task of the implementation phase is translation of the algorithm into the programming language, in our case C++, and initially this will be a very frustrating process for you because you're learning the syntax or the grammar of C++. This gets a lot easier as you program and gain experience with the syntax of the programming language, the errors generated by the compiler. And I will tell you that learning a structured programming language is a great cognitive exercise. It helps to develop problem-solving skills that will serve you so well way beyond the scope of this course. You may not understand that at this point in time, but just trust me. The process of debugging a program is a very analytical, cognitive process that will help you tremendously in almost every aspect of your life. So, let's get back to the slide. You compile a source code, you locate errors, and using the programming language, you repair or adjust, correct those errors. You run the program on sample data to verify the correctness of the results. If you're to subtract A from B and you accidentally subtract B from A, which is easy to do, you want to take some sample data and run the program with sample data to make sure you get the results that you expect. And the results may require modification of the algorithm and the program. It may not just be a syntactical or logical error in the program. Your original algorithm may be flawed. So you may go back to the planning phase from the implementation phase if you find a problem that was not anticipated in the earlier phase. And that's okay. That's a good thing for you to experience. This slide does a nice job of flowcharting the program design process, and you see the clear delineation between the problem-solving phase and the implementation phase. At the start of the problem-solving phase, you define the problem, and then you design an algorithm. And sometimes when designing the algorithm, you realize that there's some parts of the problem that are not clearly defined. So it's an iterative process. This is called a waterfall model, where you can go back a step and redefine the problem, and then come back down to the algorithm design, and ultimately you do desktop testing. But the algorithm design ends the problem-solving phase, and it is the input for the implementation phase, where you translate a fully vetted algorithm into, in our case, a C++ source code file. And then you test it, and you'll find problems, and you go back and you change those problems. You go back to the editor and you modify the program, and you continue testing until you generate a working program. This is the first of many times that you'll hear the term object-oriented programming. Object-oriented programming has been around since I believe the mid or late 1980s. I was first introduced to object-oriented programming in the early 90s. It's abbreviated OOP, Uh, Many modern programs use an object-oriented programming approach. The program is viewed as groups of interacting objects, and each object contains algorithms to describe its behavior. And the program design phase involves designing objects and their algorithms and how they will interact with the other objects. This is the first of many, many, many references to object-oriented programming we will have in this class. Don't panic if this is foreign. It should be, will be, and we will continue to chip away at this concept. But please don't panic. I somewhat disagree with the author getting into these topics at this point, but I'll cover it. Some characteristics of object-oriented programming: encapsulation, inheritance, and polymorphism. Please, these are complex terms, and please don't panic, really. Just relax. When the time comes for us to address these, we will in detail, and I will answer many questions. And this is not something you really need to understand at this point in the class, but I'll just mention them. Encapsulation deals with information hiding, and each object contains its own data and methods or algorithms. Then there's the concept of inheritance, writing reusable code where objects can inherit characteristics from other objects. And polymorphism. A single name can have multiple meanings depending upon its context. Just park those aside. Just remember having heard them, but please don't be concerned and don't start Googling these. Well, you can, really can, but these are not topics that you should understand at any level of detail at this point in this class. If you've taken computer literacy at another college or at Camden County College, you've been exposed to the software development life cycle. Software has a life cycle, and there are some phases: the analysis and specification phase, where you define the problem, then you design the software, object and algorithm design if you're doing OOP, implementation, which is the coding, then the maintenance and evolution of the system as the organization's needs change or technology advances. You may have to go in and revise the program and have a new version of the program that you wrote initially to address new user requirements. And ultimately, most programs, and I say most because we haven't seen obsolescence for every program that was ever written, but most programs do meet an obsolescence point where they're retired and replaced with some other program. This slide concludes section 1.2. We're not finished chapter 1 yet, but here's some questions you should be able to answer, and if you can't, I would go back and review the slides. Of course, you've read the chapter before reviewing these slides, correct? Please adhere to that request. I'm one step shy of begging you to read the chapters before reviewing these lectures. So, can you describe the first step to take when creating a program? Define the problem. Can you list the two main phases of the program design process? Sure can. Can you explain the importance of the problem-solving phase? Can you list the steps in the software life cycle? We have two sections left in Chapter 1. This section covers an introduction to C++, the programming language we will spend the majority of this class learning, using as the structured programming language of choice. Where did C++ come from? C++ was derived from the C language, which has been around forever. I think I mentioned earlier, I learned C++ in the early 1990s. I had previously programmed in Fortran and assembly and some other things, some proprietary languages, but I did not learn C before I learned C++, which was not a problem for me. C++ was derived from the C language. C was derived from the B language. I wasn't even out of high school then. B was derived from the BCPL. We're talking very, very beginning of program language development. Why the plus plus? Plus plus is an operator in C++. It's an increment operator, and it results in a cute pun. That's really why they called C++ C++, because someone like the plus plus operator functionality that was written into the C++ compiler that obviously wasn't available in C, and it became part of its name. The C language was developed by Dennis Ritchie at AT&T Bell Labs in the 1970s. I was in elementary school. It was initially used to maintain Unix systems, and there were a lot of commercial applications written in C. C++ was developed by Bjarne Stroustrup, who is now a professor at Texas A&M. He's probably around 62. I think he was born in 1950, but don't quote me on that. I used to know a lot more about that when I started studying C++. I read about him. But he worked for AT&T Bell Labs in the 1980s, and C++ was an object-oriented programming version of C, and it overcame many of the shortcomings of C with the object-oriented programming approach. C still remains a subset of C++, so the commands in C are all included in C++. So the learning curve for a C programmer to learn C++ was not that dramatic, and it became wildly popular. This slide shows the beginning and ending of a simple C++ program. You have your include statement. IOStream is an include directive required for input-output commands. Namespace standard is a command saying we're going to use the standard namespace, which we'll get to in depth. And then there is a statement called int main. That is the main program. It returns an integer value, and then you see the bracket. And the statements between that bracket and the open bracket and the closed bracket are the main part of the program. And that could have 5 steps. It could have 50,000 steps. I've seen some very, very, very long programs, and I've seen some very, very short programs. I'm now going to show you how to get all of the source code files that are featured in your textbook. You're not going to have to write any of these if you follow these instructions. So here I am in Canvas, and in the first module I've got a link called All Source Code. You're going to download all of this source code. Now I've just done this to make sure I was ready for it, so I've got 2 of the same file. So let's cut, and let's just go over. You have to pick a course on your computer, and so I'm going to create, in my documents, I'll create a new folder, and I'll just put CSC121 support files. Okay, and I'm going to select paste. Then right click, extract all, and say yes. And then you'll have a series of folders with each chapter. I know we're about to use 1.8. And here it is. If I click into chapter 1 and I open, if I double click this, it will open in the editor. In the editor. It's not part of a project, it's just in the editor. So I'm going to just copy this in the editor, and I'm going to go to the actual project I'm currently working on, right? Which is Console Application 3, and I'm going to edit, select all, backspace, Control V, and I'm going to paste that entire program, which is display 1.8 from your textbook, into the compiler. I'll select Save All, and I will debug it. And here we go. We have the program actually running. You'll have to select the console. It may wind up minimized on your screen depending upon how you have your Windows set up. And so enter the number of pods. We'll say 20 pods, and the number of P's in a pod on average is 3. Okay, so we've got 60 P's in all the pods. And we're going to go over this in just a second, but I just wanted to walk you through this so that you know now when you get to chapter 2, there's all of the programs 2-1, 2-4 that are featured in your textbook. This is of critical importance. It really is. So here we go. We're now back to our video lecture, and I'm walking you through some aspects of a fully coded program that has input and output. This is 1.8 from your textbook. It declares variables, number of pods, P's per pod, and total P's as integers. And then it has a series of prompts. Press enter after press return after entering a number, enter the number of pods, and then it will solicit via the cin object number of pods. Now before we go any further, this is a very complex program to be looking at this early in the class. I don't expect you to run any of this. To write any of this at this point in time. We will get to the point where we're writing programs of this level of complexity and beyond. But I just want you to follow through and see programs that were already written, that are already debugged, and how they run. And you'll see a sample dialog. So as we progress through the class, when in the video lecture we come to display 1.8, or you're reading the textbook, and this is display 1.8, I can't remember what page it is on whatever, in chapter 1, you know that you have access to this code and you could download it very quickly, paste it into an existing project, and run it without any problems.
Now in the next few slides, we're going to drill down in extreme detail each of the components of the program we just saw a sample dialog for. So these first few statements include IOStream using namespace standard, int main, and then the open bracket is a way of saying the program starts here. Then you had a variable declaration line. Variables are storage locations that can hold values. So we defined 3 variables, and they're ints, integers, whole numbers. And their names are number of pods, comma, P's per pod, comma, total P's. This identifies names of 3 variables to store numbers. Int means the variables represent integers or whole numbers. the program statement cout and the output operator, those two left pointing arrows, or is that the less than sign, and then in quotes, press return after entering a number, \n. We'll get to that in a second. Escape character n. That's a new line. Cout is used for output to the monitor. And the two left pointing arrows inserts press a number, escape n, in the data bound for the monitor. Think of cout as a name for the monitor, and the operators point to where the data is to end up. The escape n causes a new line to be started on the monitor after that statement is output. Please, please, please do not panic. I know we're diving right in, but we are going to spend a lot of time explaining all of these statements. cin is used for input from the keyboard, and you can see the arrows are pointing the other way because you're receiving input, and that input, which is typed on the keyboard, I believe the first number was 10 pods, was it? Or 10 pods, was stored in the variable, the integer variable number of pods. The extraction operator extracts data from the keyboard. Think of cin as a name for the keyboard, and the two arrows points from the keyboard to a variable where the data is stored. Here we have a program statement which executes or performs a computation. It's processing. Remember, input, processing, output. And this takes the integer variable called total p's, and it assigns it the result of the multiplication of number of pods, which was 10, and p's per pod, which using cin received a value 9. So 10 times 9 is processed to equal 90, and that number, that integer number, is assigned to total p's. In this statement, we're using cout to send not a message, because if it were a message, it would be in quotes. I could say cout, enter another number, that would be a prompt. But in this particular case, we're using cout to send the value of the variable named number of pods to the monitor. And we typically precede that with some sort of a prompt using cout. From a program layout standpoint, C++ is very forgiving. The compiler accepts, I won't say almost any, but many patterns of line breaks and indentation. And the programmers format programs so that they are easy to read. As a programmer, you may write a program that goes into production, and then you get another job at another company, and someone comes along and needs to revise that program because the requirements change, and they need to be able to easily read the program that you wrote and understand it. We place an opening brace and a closing brace on a line by themselves. We don't have to do that, but it makes it easier to read. We indent statements so that they're easier to read, and we only use one statement per line so that the program is easier to understand. You must declare your variables, like those 3 integer variables, before they're used in the program. So typically, and not as a necessity, but you want to declare your variables at the beginning of the program. All statements in C++ end with a semicolon. You have your include directives at the beginning, and we had #include IOStream. It tells the compiler where to find information about items used in the program. These are pre-compiled object code items for input and output. IOStream is the library containing definitions of cin and cout, so we don't have to write those definitions along with our program. They are pre-compiled object code that gets linked to our program. when it's compiling. Using namespace standard tells the computer to use names in IOStream in a standard way. And we'll get to more on that later. To begin the main function of the program, we use the statement int, stands for integer, main, and then left and right, parentheses, and then the open bracket. To end the main function, we return a 0. Remember, main was looking for an integer value. We return 0, and then we close the bracket, and more of that later. And we will get to some functions that don't return a value later, but return 0 is just part of the ANSI standard, American National Standards Institute standard for the main program in a C++ project. I put this slide in to help you better understand using namespace standard. Explained as simply as possible, namespaces allow us to group a set of global classes, objects, and/or functions under a name. If you specify using namespace standard, then you don't have to put the standard : throughout your code. The program will know to look in the standard library to find the object. Namespace standard contains all the classes, objects, and functions of the standard C++ library. So below, and that probably still doesn't make sense to you, but without namespace standard, here's what that code would look like. Whenever we use the cout statement, we'd have to put standard : cout. If we use the namespace standard, we don't have to use that. And it's probably beyond the scope of this course, but there are alternate namespaces that can be designated, and we'll briefly describe that later, but that's really an advanced topic beyond the scope of this course. We are going to write C++ source code with an editor, a text editor, and the file type is .cpp, and the compiler on your system will convert the source code to object code, and the linker combines all the object code into an executable program. The definitions for cin and cout, which are already compiled into object code, will be combined by the linker, and then we will have an executable program at the end. I know I've been talking way too much, and you're thinking, I thought this was going to be a programming class, and I'm listening to this nerd ramble on and on and on, and I apologize for that. But here we are. We're going to write and run our first program, albeit very, very, very simple. I need you, and in the next slide I'll show you the code, and what I suggest is you type it in yourself. Or you can get it from the web study timeline. I put a link with the code, and you can copy and paste it. This is a critical step. Don't overlook this. Please stop, type the code into the compiler, run it, and make sure you get the output shown in the next slide. I've included several video tutorials in the first timeline session that will show you how to get into Visual C++. This is really, really important that you do this and not blow this off. If you have any problems, contact me. This is the end of 1.3, and then we have one more section, testing and debugging, and then we'll be done chapter 1. So please run this project. You'll see the code in the next slide. Hold on for just 1 second. Here's the code I want you to type into the C++ editor, compile, debug, adjust if you have problems. It's a very, very simple program that outputs testing 1, 2, 3. That's all it does. If it runs successfully, a window will pop up and you'll see testing 1, 2, 3. This should not be a problem for you, but please go through the process of doing this so you become familiar with how the compiler, the editor, and the compiler work. Thank you. As I mentioned earlier, this concludes section 1.3. We have one more section to go, and we'll be finished chapter 1. Some questions you should be able to answer. Can you describe the output of this line? C out. And then it outputs literal. Literal because of the quotation marks. C++ is easy to understand. Will be output to the monitor. Explain what this line does. C in P's per pod. Well, P's per pod is a variable. There's no quotes. Using input from the keyboard to initialize the value of P's per pod. P's per pod had to have been declared as, I believe in the program we were looking at, was an integer variable. Had to be declared before we use it, or you'll get an error from the compiler. And what does the include IO stream do? That's the include directive, which includes all the program object code for C in, C out, the input and output streams. Very briefly, we'll cover 1.4, testing and debugging. We only have a few slides, but we are going to spend an inordinate amount of time in this class testing and debugging programs. It's probably 75% of what we will be doing, or the work that you'll be doing. I'll be doing it along with you. I've written all these programs, compiled them, etc., etc. But this is the bulk of the class, testing and debugging programs so that you get them to run. Let's start off with some basic terminology. A bug is not an insect. It could be, but not in this particular context. It is a mistake in a program. Debugging is the process used to eliminate mistakes in your programs. It's a term used when a moth caused a failed relay on the Harvard Mark I computer. Grace Hopper and other programs take the moth in a logbook stating first actual case of a bug being found. Ha ha. I don't think I was born when that happened. And I'm not a young man. I'm not that old though. 3 types of errors we'll be trying to resolve in programs. Syntax errors are violation of the grammar rules of the language, and they are easily discovered by the compiler. The error messages may not always show correct location of the errors, and we're using my programming lab in this class, and that will help us with some of these syntactical errors. Runtime errors are error conditions detected by the computer at runtime. The most common is a divide by 0. You enter 2 values and it causes a divide by 0 error, which causes the computer to go crazy. Logic errors are errors in the program's algorithm. These are the most difficult to diagnose because the computer doesn't not recognize them as an error. It just outputs incorrect results. And that's why you have to test the program with known input and anticipated results to detect logic errors. If you're supposed to divide A by B and you actually divide B by A, well, the computer doesn't know. And if you code B divided by A instead of A divided by B, it will still give you results. And those results may look valid, probably will look valid. We're almost done, chapter 1, and I'll leave you with this slide that has the layout of a simple C++ program. You have your startup statements, and for now, we're only going to use #include IOStream. That includes the IOStream library. Using namespace standard allows us to not have to type standard : in front of each of the commands. And then we're going to have the declaration of our main function, and that's going to return an integer. And then we'll have within the braces, we have what's called the body or the scope of main. We'll start off with variable declarations, and then our statements, and then our return 0, which is actually the integer that main returns. And at this point in time, your head is probably spinning with all these details. Don't worry. We're going to step into each small aspect of a program, step by step, inch by inch, and I'll be explaining it in much greater detail. So please, at this point in time, you should not panic. That's the last thing in the world I want you to do.
That, my friends, concludes section 1-4 and also concludes chapter 1. Some questions you should ask yourself. Can you describe the three kinds of program errors? Syntax, runtime, and logic errors. What kinds of errors the computer catches? Well, we'll catch syntactical errors. The compiler will catch syntactical errors, not always runtime errors. What kind of error is produced if you forget a punctuation symbol, such as a semicolon? That is a syntax error. What type of error is produced when a program runs but produces incorrect results? That is a logic error. And that, my friends, is the end of your first audio lecture for this class. I always feel funny because I talk a lot, and I teach the majority of my classes in the classroom with students, and there's a lot of interaction and questions. So I know that this might not be ideal for many of you, but is the best method for me to get the material to you in a fashion that is acceptable for online or hybrid classes. Thanks. Have a great day. See you when we start the next chapter.